have one or more sectors that use the default manufacturer keys. So there's some keys that the manufacturers, when they build the silicon, there are some default keys for all the sectors. And in many applications that use MIFARE Classic systems, you don't need all of the sectors, right? If it's just a card that you use for a copy shop or something, the copy shop doesn't need to store 4 kilobits of data on the card. They just want to store your customer number or something. It's not 4 kilobits in size. So what do? They only use a single sector of the card, and all the other sectors remain at the same manufacturer default key. If that is the case, you can break the keys very easily. There is one particular attack where you authenticate to one sector using the known manufacturer key, and then you escalate from there by authenticating against a different sector. And that's a very, very quick attack. Has been publicized. There are open source tools for it. So the first try I made was, of course, to look at whether the EasyCard on any of the sectors uses a default key. Unfortunately, it does not. Well, fortunately for them, unfortunately for me. So there is a different type of attack. It's called the dark side attack. I'm not quite sure why the author called it that way. There's a paper by Nicolas Courtois, and yeah, it's generally referred to as the dark side paper. That paper is public, and it describes how it works. And there's an open source implementation called MFC UK. You can probably understand why that is. And it's the MIFARE Classic Universal Toolkit, of course, as it's pretty obvious from that name. The hardware you need for doing that is basically, well, MFC UK is a program that will do the key recovery using libNFC. libNFC is lib near field communication. It's a library that can talk to a number of RFID readers from various different vendors that all use the same ASIC, the same actual chipset for the protocol. The cheapest reader you can find new costs you about 30 euros. So you need an NFC-supported RFID reader, 30 euros, install libNFC, install MFC UK, and then you start the program, and you can start to recover the keys. It took about 3 hours to recover all the 32 keys. That's sort of, you know, the massive amount of time it needs. And the attack time could be much shorter if you were using more expensive hardware on the reader side. This attack, the attack is based on the fact that the random numbers generated by the card are not really random. They're deterministic, and they're only determined by the amount of time passed from powering up the card until you send the command. So by always powering it up and sending the same command at the same point in time, you can make, you know which random number the card will have, and you know it's always going to be the same random number. So in fact, it is not a random number at that point. And doing this over, you know, USB attached, all in software on the PC over USB attached peripheral, the timing you can do is not, you know, timing accuracy and the latency over USB from software through the operating system onto the reader is very, you know, suboptimal, so you cannot do as many cycles as you could do with something like the Proxmark, which is a specific, more research-oriented RFID reader, where inside the FPGA and the microcontroller there, you can implement all this, and it has been implemented in the firmware, and you can do many more cycles. So I haven't tried it, but you can get the attack time. If I would guess, I would say, you know, you should be able to get it down to half an hour or even less. And that means you put the card, you know, any random card, you put it there and it will do its job, and afterwards you have all the keys for all the sectors. Now, next thing is we have recovered the keys. Obviously, we want to read what's in the card. Once the keys are known, the full data content of the card can be dumped. We can just read all those 1024, 4096, whatever amount of bits it is. There's a software program called NFC MF Classic program. It's just part of the libNFC, where you tell them these are the keys, now give me a complete dump of the card. Again, the reader you use is the same reader. And after you do that, you get something that looks like, let me just open just a second. I'm going to increase the font size, don't worry. Get something that looks like, oh, this is still not. All right, this is the hex dump of the card content. So it looks something like this. You get lots of hex numbers. You don't really know what they mean because all you get is a raw dump of the card, of course. So we can see, there's, some blocks that are completely zeroed out. Here again, we have lots of zeroed out blocks here is an entire sector. A sector is always 4 blocks, is also completely zeroed out, and we find more zeroed out sectors if you go towards the end of the card. It's always only 0. Okay, so we see some hex numbers here after we have read the card. Sorry for that. Too many desktops. Virtual ones, of course. Where did it go? Oh, I think, now I know what happened. Stupid me. There we go. Sorry for that. Around here. Yeah. Okay, so we use that, we read out the card. Now we need to understand how is the data organized on the card, right? So the logical approach to this is you do individual transactions, like you go into the subway, you read it before, you read it after, and then you compare what has changed in the data. And you do that again, you leave the subway station and you look what has changed again. And you make a purchase, you recharge the card, you go into a bus, you rent a bicycle and so on. You do all these things and all the time you do captures, you reread the card again and see what's happening. In the subway station, that's, there's always video surveillance, so it might be a bit suspicious if you walk through the toll gate and you unpack your laptop and you have your reader and stuff. It might be a bit suspicious, especially considering, well, there's both video surveillance and there's always a guard at every station. There's no unmanned stations. So, but the other thing is that many subway stations, inside, after you've passed the toll gate, there's a public bathroom. So you can go in there, you plug in your laptop and your MIFARE reader, and then you can read the card again. Very convenient. No video surveillance there, not that I can tell. You look at this and you repeat it with all kinds of transactions. And what you end up with is, well, we can do something like, this is actually post-entry. So after entering the subway station, and I can now do something like diff the hex dumps of, I went into a station, made a dump, and then I left the station again and made a dump again. And then you look at the diff, and you see something like this, a lot of stuff is the same, but this has changed here. And you see this, 0x190, which if you convert it is something like, is 400 NT dollar, which happens to be the initial value after you've purchased the card. Right, 400 is the value. I said you pay 500 NT dollars, you get 400 credit, and so on. And then you see it gets replaced by 184, which means entering and leaving the MRT station has just cost you 12 NT dollars, right? Because now it's 388. So you have already found, by only looking at the first diff that shows up in the hex dump, you already see that this is very likely to be the amount that has been changed. And you see it has been changed here, right? This was 190, it has been changed to 184, has been changed over here, and you see some strange stuff over here, which happens to be the inverted value. So if you do something like, anyway, it's, it's FFFF minus the 100, minus the respective amount. So it's just an inverted, a bit inverted storage. You see some other changes down here. So 001 has been changed to 002. 5 has changed to 1. It's not really clear what that is. A line with zeros has been replaced with a lot of other stuff. And there are more changes further down the road, which are not really clear at this point. But this is just to illustrate the actual steps that I did. Okay, now doing this with lots of transactions, you actually get an idea. Things change here, things change there. Then you enter the same MRT station using the same toll gate, and you see, some numbers are the same. So this must be the specific reader identifier or the station code that represents that particular MRT station, and you start to get a feeling of what happens. And it turns out there's a number of different things that you can find. Sector 2 is what we've just looked at in the hex dump. It's the balance. So this strange storage format of having twice the same value plus once the inverted value actually is what's called a MIFARE value block. This is a feature of the MIFARE card itself where it is intended, you have this block, it represents the value, in this case 400 NT dollars, and you have two different keys. One key can always only decrement the counter, and the other key you can write it. Now, given the fact that the keys are very easy to recover, of course, it misses the point. But at least until people have figured out how to recover the keys and do the cryptographic attacks, this was how the system was being designed. And the inverted storage is so you cannot flip single bits and make it work. So you have the backup copies and the inverted one, which means if you use like ultraviolet, right, or something on the EEPROM or flash storage, then you can only switch the bits in one direction but not the other. So by storing it, the value and the complement value, if you would use light or anything like that, or to flip bits in the hardware, you would not be able to have a consistent reading again after you did that. So that was the idea of this system. Yeah, the value, as I said, 1-to-1 represents the account balance of the card in NT dollars. It's not really anything else about that. There come some other sectors which I have discovered to be the transaction log. It contains log information. The number of the last couple of operations that this card has been done, stuff like a transaction identifier, the cost, like the amount of money that was involved, the remaining balance, at which particular MRT station it happened, the RFID reader ID, was it entering the station, leaving the station, connecting is again a different operation, or purchasing something in cash, or actually recharging the card using a recharge machine. There's a timestamp associated, which conveniently is a 32-bit Unix time format in seconds since the epoch. However, it refers to Chinese Standard Time, not to UTC. So yeah, otherwise it's the same. I was a bit surprised to see it like this, because in Taiwan, the calendar starts in 1911, right? So right now we have the year 99, but they still use Unix timestamps here. So probably not enough political influence on the manufacturer. The MRT station code, how do we decode it? I mean, for adding money to it is not really important, but I wanted to understand what's going on. So it's the MRT station code. So you see, if you go to one station, you have 10. You go another station, you have 12. Now, you could go to each and all of the stations, and then you create your mapping. This is the station name in English, in Chinese, and that's the hexadecimal number that represents it on the card. Would be very tiresome. What was actually much easier is to go to the homepage, which has a nice map of the MRT system, and you put your mouse onto one of these station names, and in the URL line, the last 3 digits is the station code. In decimal, though, you still need to convert it to hex. Okay. Now, there's another interesting block or sector, it's sector 7, that contains the last MRT entry or exit record, which is, it contains the MRT station code and a timestamp. And it's used to compute the sort of, how can I say, it's not distance, it's difference, or, well, anyway. So when you switch from subway to a bus or switch between subway lines, then there is a discount. It's not as expensive as doing a bus ride and an MRT ride. And using the information in there, they discover, what kind of means of transport have you used last and when was that? Are you eligible for the discount? There is a maximum daily spending. You cannot spend more than 3,000 NT dollars per day with the single card. You can charge up to 10,000 on the card, but the daily limit is 3,000. And in sector 15, block 2 at offset 3E0, you have a record that contains the amount of money you have spent on a given day of the month. So it contains the day of the month. So let's say today is whatever, 29th. So it would mean 29, and you've spent whatever, 1,000 NT dollars so far on that day. And this is checked in all the transactions. And if that value reaches 3,000, the card is refused from any further transaction, as long as the day of the month is the same. Using the scheme, as far as I understand it, if you were to wait exactly until the same day of the month happens next month, you would not be able to use the card. But I'm not entirely sure. Maybe there's something in the data format that I didn't understand, and I wasn't there for a month at that trip to actually validate that. Now,